Is going to go over the solutions to the tutorial problems for topic 7, how does a speed camera work? 1. In this problem, we're told that a person is sitting in a kayak out at sea. They rise and fall as the waves pass them. They notice that the period of the waves is 1.2 seconds. And here's the waves going past. Here's the person in the kayak going up and down. And that the wavelength is equal to 6.2 meters. And part A of the question asks, what is the frequency of the wave? Well, to calculate the frequency is the inverse of the period. So that's 1 divided by the period. So 1 divided by 1.2 seconds gives us 0.83333, and the units for frequency are hertz, or you can put it as inverse seconds if you want. Now, this is just to two significant figures, so we should give our answer to two significant figures, so 0.83 hertz. Now, part B says, what is the speed of the wave? In order to answer this one, we're going to need to use our equation V is equal to F lambda, where F is the frequency and lambda is the wavelength. So we now got the frequency, so we've got 0.83333 times the wavelength, which is the 6.2 meters, and this gives us a speed of 5.167 meters per second, but we should just give our answer to two significant figures, so this is equal to 5.2 meters per second. Problem 2. So we're told that a radio tower sends out a radio signal with a wavelength of 2 meters. So here's the radio tower, and it's sending out signals, and the wavelength is equal to 2 meters, 2.0 meters, so two significant figures. And part A says, what is the speed of radio waves? Well, in order to answer this one, we need to realize that radio waves are just electromagnetic radiation, and all electromagnetic radiation travels with the same speed. So the speed is equal to the speed of light, which is 3.00 times 10 to the 8 meters per second. This is going through air. Air is very close to a vacuum, so light travels at almost the same speed in air as a vacuum. So this is the correct answer. Part B says, how long does it take for the wave to travel 2 kilometers? So we know that time is equal to the distance over the speed. So this is equal to 2 kilometers, which is 2,000 meters, over the speed, which is 3.00 times 10 to the 8. And so this gives us, when we solve it on the calculator, 6.667 times 10 to the minus 6 seconds, which to two significant figures is 6.7 times 10 to the minus 6 seconds. We would expect a very small number here because light travels very, very quickly. So it doesn't take light very long to travel a short distance like 2 kilometers. Part C asks, what is the frequency of the wave? Well, to answer this one, we'll need to use our wave speed equation, V is equal to F lambda. We can rearrange this one to get the frequency. The frequency is equal to the speed over the wave over the wavelength. The speed is 3.00 times 10 to the 8, and the wavelength is 2 meters. And so this gives us 1.5 times 10 to the 8 meters per second to two significant figures. Part D asks us, what is the period of the wave? Well, the period is equal to 1 over the frequency, the inverse of the frequency. And so the period is 1 over 1.5 times 10 to the 8. And so the period is 1 over 1.5 times 10 to the 8. Whoops, we've got the wrong units here. This should be the units for frequency because it's the frequency we've found. So this should be inverse seconds or hertz, not meters per second. So this is 1 divided by 1.5 times 10 to the 8 hertz. And solving that on the calculator, we get 6.7 times 10 to the minus 9 seconds is the period. Problem 3. In this problem, we're told that seismologists can locate the position of the epicenter of an earthquake by comparing the arrival time between two different types of waves at 3 locations. These waves are primary waves, or P waves, with a speed of 4,800 meters per second, and secondary waves, S waves, with a speed of 2,900 meters per second. And part A, we're told that P waves are longitudinal waves, and we're asked to use a diagram to explain what a longitudinal wave is. Okay, so let's draw what happens to particles as a longitudinal wave passes. So we get compressions and what's called rarefactions. And the distance between two compressions is the wavelength of the wave. And what makes this a longitudinal wave is that the particles making up the medium are displaced in a direction parallel to the movement of the wave. So the velocity of the wave is in this direction, and these particles move backwards and forwards in the same direction, parallel to the velocity of the wave. Part B asks us, S waves are transverse waves. Draw a diagram showing what a transverse wave is. Okay, so a transverse wave looks like this. The particles move up and down, and the velocity of the wave is in this direction. This is one wavelength here. So the particles making up the medium through which a transverse wave travels move perpendicular to the direction the wave travels in. And now part C. We're told at one base station the P wave is detected 3.5 seconds before the S wave. So we know that TP is less than TS as the P wave is detected first, and we can write an equation with this information in it. The arrival time of the S wave minus the arrival time of the P wave is equal to 3.5 seconds. Let's call that one equation 1. And we're asked, what is the distance of the base station from the epicenter? We know that distance is equal to speed times time. So we've got that the distance is equal to the velocity of the P waves times the time it takes the P waves to travel to the base station from the epicenter. And we also have that the distance is equal to the velocity of the S waves times the time it takes the S waves to travel to the epicenter. So what we can do now is equate these two together, because this is the same distance. This is the distance from the epicenter to the base station. So this tells us that VP TP is equal to VS TS. And so TP is equal to VSTS on VP. Now let's call this equation 2. And what we can do is substitute equation 2 into equation 1. So sub 2 into 1. So this tells us that TS minus, instead of writing TP, we'll put VSTS on VP is equal to 3.5. So rearranging this, we can pull TS out as a common factor, and we've got 1 minus VS on VP is equal to 3.5. Okay, we need to make some more room. We'll continue up here. So we've got TS is equal to 3.5 divided by this, which is 1. Now, VS, the velocity of the S waves, we're told is 2,900, over the velocity of the P waves, which is 48,000. And so this is equal to 8.84 seconds. The question has asked us to find the distance, so what we can do is now substitute back into this equation here to get the distance. So the distance is equal to 8.84 times the velocity Vs, which is 2,900. So this is equal to 25,642 meters, which is equal to 26 kilometers to 2 sig fig, which is scarily close, really. So if you wanted to check this, what you could do is work out what TP was and just check that that gives you the same answer as well. Now, to do part D, let's just clear some more space. So part D asks us, can you think of a reason 3 base stations are required to pinpoint the epicenter? If we have 1 base station, then we know that the earthquake epicenter is a certain distance away. So it can be anywhere here. We could work out what this distance here was. This is base station 1. And so we know that it's somewhere on a circle. If we have 2 base stations, so here's base station 2, and this has got some other D, so we know that the earthquake is some fixed distance from this base station, which tells us that the epicenter could be here or here. We don't know. There's 2 options. Both these options satisfy the requirements. There's actually a few more than 2 options if we consider that the epicenter could actually not be on the surface of the Earth. It may be below the surface of the Earth, in which case, rather than just being circles, these are spheres. And so wherever these intersect, that's an option for where the earthquake came from. But if we have a 3rd base station and we measure the distance from this base station and we know it's this distance here, let's call this D3, then we know at which point the epicenter is, because there's only one point where all of the 3 spheres or circles intersect each other. Problem 4. So in this problem, we have a low density medium with a pulse traveling along it, and it gets to a higher density medium here. And we're asked what happens once the wave gets here. Well, a couple of things happen. First of all, some is reflected and some is transmitted. The transmitted pulse, as this is a more dense medium, is going to have a smaller wavelength. So it'll be a bit compressed up like this. So going to travel slower through this medium. When it gets reflected off this end here, because it's being reflected off a more dense medium, it's like being reflected off a fixed end. So it does undergo a phase change and it actually comes back underneath. So this wavelength should be the same as this one. And then in the second figure, we have a pulse going through a more dense medium and then getting to a less dense medium. and we're asked the same thing. Some of it is transmitted through this less dense medium. It has a longer wavelength than the less dense medium and travels faster. Longer wavelength, and some of it is reflected. When it's reflected off a less dense medium, and so it doesn't undergo a phase change. So it's reflected back on the same side of the string. So these two should have the same wavelength. This wave is travelling in this direction and this one's travelling in this direction. So that's everything we can say about that question. Problem 5. This problem says that you're cycling along the road at 30 kilometers per hour. So here's you cycling along. Your velocity is equal to 30 kilometers per hour, which is equal to 30 times 1,000 over 60 times 60, which is equal to 8.33 meters per second. When an ambulance comes up behind you with its sirens blazing, so here's the ambulance behind you, it has a speed of 90 kilometers per hour, which is 90 times 1,000 over 60 times 60, which is equal to 25 meters per second. Now you hear a frequency, f dash, of 800 hertz. And in part A, we're asked what frequency do the people inside the ambulance hear. So these people hear the frequency of the source, which is what we give the symbol f to. So our Doppler equation is f dash, the frequency observed by the observer, is equal to f, the frequency produced at the source, v plus or minus VO, so this is the velocity of the observer, and this is the velocity of, in this case, sound, because it's sound waves, and this is over V minus or plus Vs, and this is the velocity of the source. And we take the top sign if they're approaching and the bottom sign if they're receding. So in this case, we know what f dash is. F dash is the 800. So we've got 800 is equal to the frequency of the source, which is what we're trying to find. Now, in this case, the observer, you on the bicycle, are moving away from the ambulance. And so we'll need minus VO over, and now in this case, the ambulance, the source, is approaching you. So we've got V minus Vs. So let's substitute in. We've got 800 is equal to F, and the velocity of sound in air, we're told, is 343, minus VO, which is 8.33 over 343 plus 25. And so this is equal to F times 1.052. And so F is equal to 800 over 1.052, which is equal to 760 hertz. And now part B, so this is the frequency which is actually produced by that siren. Part B says once the ambulance has overtaken you, so now it's in front of you. Here's the ambulance over here, still got the same velocity. We're told to assume that we all keep moving at the same speed. What frequency do you hear now? So in this case, we'll have f dash, we're trying to work out the frequency you hear, which is equal to the frequency at the source. Now, in this case, you are now approaching the source. This is the source, this is you, the observer, and so we have V plus V observer over, and now in this case, the source is receding from the observer, and so we need to take the bottom sign, the positive sign. And so substituting in 760, 343 plus 8.33 over 343 plus 25. Solving this on the calculator, we end up with 725 hertz. And so we can give this to two significant figures as 720 or 730 hertz. Either of those would be fine. Problem 6. So in this problem, we're told that two submarines, sub A and sub B, approach each other in a training exercise. Sub A, so sub A is the source, it sends a sonar signal with a frequency of 1200 Hertz to sub B. The sonar signal travels through water with a speed of 1,500 meters per second. So sonar is sound, but it travels a lot faster through water than through air. One of the reasons is that water is more dense than air. If sub A is travelling northwards with a velocity of 8 meters per second, so V of the source is equal to 8.000, and velocity B is travelling southwards because they're travelling in opposite directions, so V of the observer is equal to 6.000 meters per second, then we're asked in part A, as they approach each other, what frequency does sub B detect? So we're going to need to use our Doppler equation. F dash, so the frequency detected by the observer, is equal to F, the frequency produced by the source, over V, the velocity of sound in the medium, which in this case will be 1,500, plus or minus the velocity of the observer over V, minus or plus the velocity of the source. Now in this case they're both approaching each other, so for both of them we use the top sign. So we've got F V plus VO over V minus Vs. Okay, so now we can substitute into this equation. The frequency of the source is 1,200. The velocity of sound in water is 1,500. The velocity of the observer is 6 over 1,500 minus the velocity of the source, which is 8. And then solving that on the calculator, we get 1,211 Hertz, and that's to 4 significant figures, as everything's given to 4 significant figures. Now in part B, we're told that after passing and narrowly missing each other, so here's sub A, it continues travelling this direction, and here's sub B, it continues to move in this direction, and we're asked, now that they've passed each other, what frequency does B detect? So in order to answer this, we're going to have to go up to this equation here again. Now in this case, they're both receding from each other, so we need to choose the bottom symbol. So we've got V minus VO over V plus Vs, and now here's our observer, so this is equal to 1,200 times 1,500 minus the 6 over 1,500 plus the 8, and solving that one on the calculator we get 1,189 Hertz, and that's to 4 significant figures. Problem 7. This one's quite challenging. Bats chase down their prey by sending out ultrasonic sound signals and then listening to the echo. This gives them information about their distance from the prey and the speed of the prey is travelling at. If a bat travels at 5 meters per second, okay, so here's our bat. It's travelling with a speed of 5.0 meters per second. It emits a chirp with a frequency of 40 kilohertz, and then it detects the reflected chirp with a frequency of 40.4 kilohertz from the insect trying to escape by flying directly away from the bat. So here's our insect. It's travelling in this direction away from the bat. And so the signal from the bat comes in this direction, bounces off the insect and comes back. Now in part A of the question, we're asked to write down an expression for the frequency detected by the insect, which we're calling F dash. Okay, so we know from the Doppler equation, F dash is equal to F V plus or minus velocity of the observer over V minus or plus the velocity of the source. Now, in part A, the source is the bat and the insect is the observer. And so just substituting in here, we've got the frequency detected by the insect is the frequency transmitted by the bat over this V stands for the velocity of sound. And in this case, the observer, which is the insect, is receding from the bat. So because it's receding, we need to use the bottom sign. So we've got minus v for the insect over the velocity of sound. And now in this case, the source is approaching the bat. So we take the top sign, which is the negative. So v bat. And so that's the answer to part A. Now in part B, it says write an expression for the frequency detected by the bat, f double dash, when it's reflected off the insect. So what we need to do now is actually now consider the insect as the source, as it's providing the reflection, and the bat is now the observer, as it's detecting the signal. And so we have f double dash, which is the frequency detected by the bat, is the frequency emitted by the source, which is this f dash. Okay, and now in this case, we've got the velocity of sound, and the observer is the bat. The bat is moving towards the source, and so we take this top sign. So this is plus v of bat. And the source, in this case, is the insect, which is moving away from the bat. So we take the bottom sign, so plus v of source. And now what we should do is, instead of having this f dash here, which is the frequency of the reflected signal, we can substitute in for f dash from up here, because these two are the same thing. So this is equal to f times the velocity of sound minus the velocity of the insect over the velocity of sound minus the velocity of the bat times the velocity of the sound plus the velocity of the bat over the velocity of the sound plus the velocity of the source, which in this case was the insect. And so that is the formula. Now part C says use this expression to calculate the speed of the insect. So now we're going to need to substitute everything in. The only unknown in this formula is actually the speed of the insect. So let's substitute everything in. F double dash, that's the frequency detected by the bat. So that's 40.4 times 1,000 hertz. F, that's the frequency transmitted by the bat. Now the velocity of sound, that's 343 minus the velocity of the insect over 343 minus, now the velocity of the bat is 5. And we've got 343 plus 5 over 343 plus the velocity of the insect. Okay, now we can divide this side by this. The 1,000s cancel out. So 40.4 divided by 40 gives us 1.01. And we've got 343 plus 5, so that's 348, over 343 minus 5, which is 338, times the 343 minus the velocity of the insect, over 343 plus the velocity of the insect. Okay, so we can move these numbers over to this side, and we end up with 0.98097 is equal to 343 minus the velocity of the insect over 343 plus the velocity of the insect, and then multiply both sides through by the denominator, and when we do that we get 336.47 plus 0.98097 velocity of insect is equal to 343 minus the velocity of the insect. Move the two velocity of insect terms to the left side and the numbers to the right side. We have 1.98097 times the velocity of the insect is equal to 343 minus 336.47. And then we can just divide by 1.98097 to find the velocity of the insect. So this gives the velocity of the insect as 3.3 meters per second. And so D, does the bat catch the insect? Well, yes, it's going at 5 meters per second. The insect's going at 3.3 meters per second. So eventually the bat will catch up to the insect. So yes. Problem 8. So in this problem, an ant, a snail and a lizard have a race. They all head northwards with speeds. So here's our ant. V ant is equal to 6.56 millimeters per second, which is equal to 6.56 times 10 to the minus 3 meters per second. And then the snail goes with a slightly higher velocity of 0.13 meters per second, and the lizard is quite speedy with a velocity of 0.500 meters per second. And in part A, we're asked what is the velocity of the ant relative to the lizard. So the velocity of the ant relative to the lizard is equal to the velocity of the ant minus the velocity of the lizard. And so this is equal to 6.56 times 10 to the minus 3 minus the velocity of the lizard, which is 0.500. Solving this on the calculator, we get minus 0.493 meters per second. So this negative means south. So this is equal to 0.493 meters per second south. So if you were the lizard, it looks like the ant is moving away from you in the negative direction, the direction opposite to what you're actually traveling. Part B, we're asked what is the velocity of the lizard relative to the snail. So the velocity of the lizard relative to the snail, so that's equal to the velocity of the lizard minus the velocity of the snail. So now we imagine that we're the snail, and what would the lizard look like? It would look like the lizard was getting further and further away from us, but in front, so we'd expect this to be in the north direction. So the velocity of the lizard is 0.500. The velocity of the snail is 0.130. And so solving this on the calculator, we get 0.370 meters per second. And as it's positive, it's in the north direction. And then finally, part C. We're asked, what is the velocity of the ant relative to the snail? So the velocity of the ant relative to the snail. So while if we were the snail, it looks like the lizard is getting further and further ahead, it would look like the ant was getting further and further behind. So we'd expect this one to be in the south direction again. So we've got the velocity of the ant is 6.56 times 10 to the minus 3 minus 0.130. And solving that, we get minus 0.123 meters per second, which we can say is 0.123 meters per second south. This is problem 9. So in this problem, you stand on the bank. So let's draw a little diagram over here. Here's you standing on the bank, and you watch your friend in a rowboat rowing across a river which is 25 meters wide. So this is 25 meters. And on still water, your friend can row at 5 meters per second. So, however, the river has a current that is flowing downstream at 2 meters per second. So we've got the river's current flowing down there at 2 meters per second, and your friend attempts to row directly across here, and that is at 5 meters per second. And part A asks us, what is the velocity of your friend relative to you? So in order to answer this question, we need to remember that velocity is a vector, so we need to work out the direction as well as the magnitude. So our friend, we see her rowing directly across the river with a speed of 5 meters per second, and then the current is affecting her speed downriver at 2 meters per second. So this angle in here is theta. So let's work out the magnitude first. We can use Pythagoras' theorem. These are perpendicular to each other. So we've got V is equal to the square root of 5 squared plus 2 squared. And so that's 25 plus 4, so the square root of 29, which is equal to 5.39 meters per second to two significant figures. We now need to work out this angle. So in order to work out the angle, we remember SOHCAHTOA. And what we've got is the opposite and the adjacent. So it'll be this TOA part that we'll use. So tan theta is equal to adjacent, which is 2 on 5. So this tells us that theta is equal to the inverse tan of 2 on 5. And solving that on the calculator, we end up with an angle of 21.8. And so the velocity is equal to 5.39 meters per second at an angle of 21.8 degrees to the line drawn directly across the river is one way to say it, or otherwise we could sketch this diagram here and say as shown in the diagram. Now for part B, we're asked how long does it take your friend to cross the river? And so we know that the velocity is equal to the distance over the time, and what we're going to be considering here is the direction directly across the river. And the reason for doing that is that we've got a length directly across the river of 25 meters. So let's rearrange this equation. We've got time is equal to distance over velocity, which is 25 over 5. So that's equal to 5 seconds. And so that's how long it takes her to cross the river. Part C, we've then got the question, how far downstream does your friend end up? So in this case, we're going to consider the direction parallel to the bank. So consider and in this case, we want to know the distance. So rearranging this equation here, we've got distance is equal to velocity times time. Now the velocity parallel to the bank is 2 meters per second, and the time is the 5. So this is equal to 10 meters downstream. And finally, problem 10. So we're told that an ultrasound device uses a signal with a frequency of 7.00 megahertz. So that's 7.00 times 10 to the 6 hertz. This signal consists of sound waves with a velocity of 1,540 meters per second inside the human body. And part A, we're asked what is the wavelength of this signal inside the human body? So in order to do this, we just need to use our wave equation, V is equal to F lambda, which tells us that the wavelength is equal to the velocity of the frequency, which is 1,540 over 7.00 times 10 to the 6. And solving this one on the calculator, we end up with 2.20 times 10 to the minus 4 meters. So a small wavelength. Part B asks us if the signal takes 1.95 times 10 to the minus 4 seconds to return to the scanner after leaving the scanner and reflecting off part of the baby, how far is that part of the baby from the scanner? So we've got our scanner, it sends out the signal and receives the reflection, and we need to work out what this distance here is. So we know that distance is equal to speed times time. So we've got the speed is 1,540 meters per second. The time is 1.95 times 10 to the minus 4. So this gives us a distance of 0.3003 meters. Now that's the distance travelled by the signal, which is actually half the distance to the baby, as the signal has to travel to the baby and then back to the scanner. So this tells you that distance to baby will be half of this, which is 0.3003 on 2, which is equal to 0.150 meters to 3 significant figures. And that's the end of this tutorial set.